Welcome back to the second part of this CNN series. In the next minutes we will talk about how we can build and train a CNN in PyTorch and how to select the appropriate architecture for our problem. Remember, we wanted to classify images containing the new 7 wonders of the world with a neural network. Before we start, let's quickly have a look at the components we need in our code. You might already know that PyTorch is an object-oriented deep learning framework. This means the functionality is separated into different classes. For our use case, we mainly need the 4 following modules, which we will build one after the other. A dataset that contains our training and test images, a data loader that can be used for iterating and batching over the data, the actual CNN model, which is made up of different neural network layers, and finally an optimizer that backpropagates the loss to adjust the weights in our model. Let's have a look at the first block. How do we load and use the dataset? So this is the Google Colab notebook we've also used in the first part of this series. There we went over how we can visualize the convolution. Now let's continue here with how we can install PyTorch, enable GPU and access the data on Google Drive. Usually you would run a pip install Torch and Torch Vision to get both Python modules. Torch Vision is the module for computer vision tasks from PyTorch. Also make sure under runtime, change runtime type, you select a GPU session. Then if you run Torch, CUDA is available, you should get a true, which means we can use the GPU. So next, if we run this cell, we can mount the Google Drive to this location. And therefore we have to access another URL and enter an authorization code. After this is done, you will get this message mounted at, and if you look at the folder structure here, we see we have this new folder here, and my data from Google Drive is now stored in this folder. So next, let's have a look at how we can load the data. Actually, we don't have to do this manually because there's a PyTorch function that handles this for us, but here we just quickly want to investigate the data we have. Let's have a look at the folder structure. We see we have a test folder and a train folder, and inside of these folders we have the different classes. And there we have the images. For example, we have 2 test images for this wonder and 8 train images. And in total we have a relatively small data set with only 80 images, 10 per label. So here we quickly define the path to our data and we iterate over the files. This is not too important, but essentially what it does, it fills a dictionary with the class type and then a list of paths that correspond to this class type. And now what we will do, we randomly select images from this set of different paths and display them to get an overview of our data. This is done in this code, so I also won't go into detail. We will use matplotlib here, and here we can see a collection, 9 images, which are randomly selected, and we can see the different types. So we can already observe a couple of things here. First of all, we have RGB images with 3 colored channels. Our shape is therefore width, height and number of channels. Also, we encounter different sizes of the images, and later we will have to normalize them. Additionally, as already mentioned, we have 8 train images per label and 2 test images per label. The PyTorch dataset class is an abstract representation of a dataset and contains at least the getItem and len methods. You can inherit from this class to build custom datasets that can be used to index the data at a central place. As image data is often arranged in different folders, we can exploit this structure to easily create such a dataset with a predefined function. So this predefined function I've just talked about is called image folder. It's stored in Torch Vision datasets image folder. And if I hover over this, we can see it expects a shape like this one. So the folder name corresponds to the class, and then we have the collection of different images. This is exactly the structure we have here. Therefore, we can use this function, we pass it the path to our root of this folder, and then this function will create a dataset for us. And if we investigate this, we see we have a dataset created from this image folder. We have for the training dataset 64 data points, so images. And if I select a sample, so the first index, I get a tensor like this one, which is the image. And the second part of this tuple is the label. So we will always get a tuple when we index the data that consists of image and label. And as you see, the labels are automatically converted to numbers. Instead of the folder name, we have a number now here, and we can convert them back later. And in the back, PyTorch uses Python imaging library to load these images. There's also another thing happening here, which are these transforms. Let's have a look at what is happening there. Pipelines are used in many places when you enter the area of machine learning. The reason for this is that you often have to perform certain pre-processing operations on the data, typically executed several times. Instead of executing each of these steps manually, a typical approach is to define such a pipeline that contains these operations in a specific order. The advantage of this is that you simply feed in the data into your pipeline and everything is applied automatically. For instance, we input an arbitrary image, and the first transformation is resizing it to a specific shape. After that, we, for instance, convert the image to a tensor, which can be used by PyTorch. PyTorch Transform Compose is doing exactly this task for us. Whenever we index any of the images in our dataset, the preprocessing steps will be applied automatically. So back in our codes, this is what is happening in this compose part. We resize all of our images to a shape of 512 by 512, and we use the Python imaging library interpolation, which is specified here, and then we convert it to a tensor. The same thing happens for our test data set, so we have exactly the same code here, except we use the test root now as root path for this data set. Next, let's talk about the data loader. They help us to efficiently load the data and improve the performance of our optimizer. Loading the data can become a bottleneck in many deep learning applications. Imagine you have 1000 images with a size of 5 megabytes. If you load and iterate over them, you already require 5 gigabytes of memory. Most standard PCs have 8 or 16 gigabytes, so you already occupy a large portion of it. Data loaders allow us to only load parts of the data, so-called batches. Typically, you take 32 samples for each batch and train the model with these. Instead of using all data, we now sample only the small subset for each iteration. The optimization procedure is therefore also called stochastic gradient descent, as we randomly sample parts of the data. It has been shown that this actually converges even faster to the minimum of our loss function in most cases. Furthermore, with data loaders, you can, for instance, shuffle the provided dataset, parallelize the data loading, or cache the data after preprocessing to speed up the loading times. So overall, a very useful class that simplifies the training for us. So we can create those data loaders using Torch utils data loader. What we do here is we simply pass the data set, so the train and test data set. We will create a train data loader and a test data loader, and we specify shuffle true, which means when we iterate over the data, it will be randomly selected or shuffled, and we choose a batch size of 8 here because we have a relatively small data set. So now that the data is ready, let's build the CNN model. There's always the question how to build such a neural network, how many layers to use, which filter size. Luckily, there are several rules of thumb to simplify the initial steps for us. First of all, building a model is a sequential process. That means most of the time the first model will be further improved as we get experience with our problem. Therefore, simply start with a basic CNN structure. For this, you can follow one of the two common patterns, either stacking pairs of conv layer and pooling layer, or stacking 2 conv layers and 1 pooling layer. For the filters, select odd sizes such as 3 by 3. The reason for this is that these shapes always have a centered pixel that preserves the location of the activation after filtering. Start with smaller filters to capture local features such as edges, and optionally increase the size in the higher layers of the network. Generally, smaller filters such as 3 by 3 should always be chosen over larger filters. The number of channels should be low in the first layers and then increase as the network gets deeper. The reason for this is that we want to capture more high-level features in the higher layers, and therefore we need multiple feature maps. The low-level features like edges are not so variant, and we can start with only a few channels. Also, the pooling layers compress our filtered representations, and we need more channels to avoid an information bottleneck. Using padding is generally recommended, first of all because you simply maintain the size of your image, but also because you keep the information at the border of the image. Especially if you want to build very deep CNNs, it is important to keep the dimension, because otherwise the size would reduce very quickly and you couldn't stack any further layers. For the pooling layers, we can simply use a 2 by 2 or 3 by 3 kernel and max pooling, as this works well in most architectures. Once we have a basic model, we play around with the complexity by adding layers. Of course, it is also recommended to get inspired by other popular architectures that performed well on baseline datasets. We will have a look at some of those in a second. Finally, you should also tune the basic neural network parameters such as the learning rate or the activation functions. So now that we know how to start with a CNN, let's have a look at the baseline model I created. So you can create a CNN simply by inheriting from this neural network module from Torch. And basically it's always the same pattern. You have an init function where you define your layers, and you have a forward function which will be called when we feed the data into the network. In the init function, we have this pattern. So we have two conv layers, one pool layer, another two conv layers, and one more pool. And after that, we have the fully connected part, which means we have the classifier here. And there we have three linear layers. One that takes the input of the last pooling layer and converts it to 120 neurons. And then we transformed it to a smaller size. And finally, we have 8 output units, which stand for the 8 classes we have. In the forward function, we simply stack the layers like this, and X is our input image, which will be first fed into the first convolution, then an activation function, reload activation, then the second convolution, another activation, and then the pooling, and the same happens for the second stack of these filters. And after that, we apply flattening. I will talk in a second about how this works. And then we pass the data further through our fully connected layers until we end up with the output of 8 classes. So we can have a look at the structure again. Here we get all the parameters summarized. We use a stride of 1 and a padding of 1. We start with 3 input channels, which are red, green, and blue. And then we apply 5 filters, which means we get 5 feature maps. And then these 5 feature maps will be further filtered with 10 filters, so we get 10 feature maps, and so on until we have 30 feature maps in the final layer. And we use a kernel size of 3 in those, which means we have 3 by 3 filters. And here we have a kernel size of 5, which means we have 5 by 5 filters. And we use padding for both of these. I also quickly wanted to visualize the use of flattening operations. What it does is pretty simple. Once we went through the feature extraction, so our conv pool pattern, we observe several two-dimensional feature maps. Now, how do we pass them into the input layer of a dense neural network? There are mainly 2 approaches to do this. The first option is to reshape the feature map to a one-dimensional vector. On other terms, we flatten the feature map. This means we convert the matrix to an array by taking each row or column and appending it. The length of this array is then equal to the number of neurons in the input layer of the dense network. The second option is global pooling, which is compressing the final representation. Basically, it's just another pooling operation that converts our matrix to a single value. This means we take the mean or max of a complete feature map. That's why it's called global. Typically, if you use global max pooling, you only have one fully connected layer which outputs your prediction. In fact, the global pooling layers can also completely replace the fully connected layers in the CNN. If we have the same number of feature maps as output classes in the last convolutional layer, we can apply max pooling and directly use the global pooling values with softmax for our prediction. So there's also another option how to build a CNN using this sequential module. This simply means we separate the layers with a comma and we pass them to the sequential module. And we can do this separated for the CNN and the classifier or do it all together. And the advantage is that if we call the function, we simply can use this sequential thing. And additionally, we also don't have to define variables as we did it here. And we also don't have to pass everything manually here. This makes it a little bit more compressed and easier to read. Now we only need one more thing, which is the optimizer that adjusts the network parameters to minimize the loss. I won't go into detail on how the optimizer and the loss work, but I quickly want to mention them here. A common choice for the optimizer is ADAM, which stands for Adaptive Moment Estimation. It is an advanced optimization algorithm that uses gradients to iteratively adjust the weights of the network. As loss function, we will use the cross-entropy loss, which can be used to calculate the difference between 2 probability distributions. What are the probability distributions in our case? On one hand, we have the predictions of our model after applying the softmax. These are the probabilities for the different classes. On the other hand, we have the ground truth, which is the true class of an image with a probability of 1, so 100%. The loss decreases when our network not only predicts the right class, but if the prediction also has a high probability close to 100. So here we define our loss function, the cross-entropy loss, and also our optimizer, which is ADAM. And we need to pass the parameters of our network, which we defined here, to this optimizer in order to be able to optimize the weights of this network. We choose a learning rate of 0.0001, which is relatively small. And then we continue to train our model. I created this train model function, and basically all it does is iterating over the train loader, which contains the iterator for our data set. And in this loop, we basically load the batch, we put it to the GPU, and we input it to our model. backpropagate the loss, and adjust the weights. And this is happening in this loop several times. We iterate over the data set. And I also print statistics, so the train accuracy and the losses for train and test. Therefore, I also calculate the test loss, and therefore I have a couple of additional functions here. Our model currently outputs 8 classes, and we will use the class with the highest probability. So we will apply softmax, and then we select the class using argmax with the highest probability. So here's an example. We train 14 epochs here. I also added early stopping, which means once the test loss is not getting better than the current best loss, we increase the early stopping counter. Once this counter exceeds the patience we have, which is for example 2 epochs, we finish or terminate the training. For example, here we can see the test loss. The smallest loss was 1.49, and here you can see the loss increases again a bit and starts to get worse, and that's the point where we abort the training to avoid overfitting. And here you can see the train loss also decreases from 2.10 to almost 0.4, and in a training data set we get an accuracy of 0.87, so 87.5%. In the test data set we only get around 50% accuracy. So we can also visualize how the losses behave using this function. We calculate the accuracy as how many predictions are correct. If the label that our model predicts matches the ground truth of the model, we say it's correct, and then we sum up all the correct ones and divide them by the total number of samples we used. We can visualize the loss like here, and this would basically be the point with the lowest loss, and actually we should use the weights of the model at this point, so we should always store them. I didn't do it here, so for this I will use the last weights of the model, but ideally you should always use the ones with the lowest loss. Now this code selects the next batch of our test data and then inputs this batch to our model to get the predictions. And after applying softmax, we will also get the probabilities for these predictions. We can use them now to calculate the classes. For instance, so we set the batch size as 8, that's why we have 8 values here. These are the probability values that our model predicts, and if we select the argmax again, so the class with the highest probability, we end up with this. The first one is the outputs, which means the predictions of our model, and the second one are the true labels. So you see we predict 2, and the ground truth is also 2, and so on. And we can also visualize this, so whenever the text above the image is green, it's a correct prediction, and when it's red, it's a wrong prediction. And I also put the probability values after applying the softmax here, so we can see how certain the model is about its prediction. And this is for one test batch, so for one set of unseen images. And we can see that pyramids do pretty well. We have 79% certainty here, and the same for this image, but we see overall the model is not performing very well. It's also not very certain about the predictions. This corresponds to the result we got up here, which is we have around 50% correct predictions, and that's basically what we get here. So now the question is, can we do better? How can we improve our model? One thing to consider when training a neural network is always how much data do we have. As you know, we have a relatively small data set, only 80 images, 10 for each class. Data augmentation allows us to enlarge our data set without searching for new images. Therefore, we make minor adjustments to images we already have. A simple possibility is to select only parts of an image. This is also called cropping. Another technique is to flip the image horizontally or vertically. If different colors occur in our dataset, we can also play around with the color values such as grayscaling. Alternatively, we can also rotate the image with a certain degree. These are just some simple examples we can easily add to our preprocessing pipeline. Note that there exist also more advanced techniques to generate more data, such as generative adversarial networks. But for our simple example, we will stick with these basic augmentation techniques. So in the code, we can use the transforms module we already know, because there are different classes such as random rotation, and here we pass the degree, so this will randomly rotate the image by 10 degrees. Or we can use this random resized crop, we pass in the image size to which our image will be resized after cropping, and it will randomly crop out parts of the image according to the scale information and then resize them to our original shape. Also, we can randomly, for example, horizontally flip the image. So there are many other possibilities, and you might have a look into this transforms module because there are a lot of transformations we can easily apply here in our preprocessing pipeline. So therefore, I create a new augmented train data set, and therefore I also create a new train loader that uses this augmented train data set. And note, we only want to adjust the train data set and not modify our test images, of course. Now here we can have a look at a sample. If I take the first image of the first batch, we can see we have a cropped out part. Let's run this again. We can see it's slightly rotated, maybe one more. So this is rotated as well. This introduces a little bit of variance in our image. So if we train this again, and here I disabled early stopping because there was less overfitting for this model, we can see we managed to get up to around 0.56. And here you can see it's also not overfitting. And if we again display the images as we did it before, we can unfortunately see that the predictions did not really improve. I can run this again with a new batch. So still the pyramids are performing quite well. We have better values, certainty values for some things like the Colosseum in Rome has now very good values. But overall, it's not perfect yet, to be honest. But there's room to improve, especially in the next part. We will use transfer learning to further improve our results. But now let's have a look at further CNN architectures. So now we have trained our baseline CNN architecture and played around with data augmentation to improve the results. But what if our model is still not performing as good as we expected? How should we change it? Well, you don't always have to reinvent the wheel. There have been many publications on different approaches to create the CNN architecture with the best results. And still today the modules are continuously improving. Better accuracy, less parameters, and more efficient feature extraction. These models are typically compared on the ImageNet dataset, which is a large collection of labeled images. All of these CNNs can also be loaded in PyTorch. This means you can also use one of these well-tested architectures and don't have to come up with your own design. And actually, we will also do this in the last part of the series when we talk about transfer learning. In the following, I quickly want to explain the ideas behind a couple of popular CNN architectures. There exist so many different publications that I could make a complete series on different models, but this is not the focus here. I just want to show you some examples so you get a feeling for what the experts in this area did. Let's start with one of the first popular architectures, Alexnet. It consists of 8 layers, 5 of them are convolutional layers. In total it has 60 million parameters and achieved a 47.1 accuracy on the ImageNet dataset. So overall not many new things here. We can see that the feature extraction part is a mix of convolution and pooling layers, as well as a couple of fully connected layers similar as we did it in our baseline model. Alexnet uses the ReLU activation function and overlapping pooling. Furthermore, the first 2 fully connected layers use dropouts. Let's have a look at what dropouts are. The basic idea of dropouts is to randomly drop out units, so neurons in the network during your training. As a result, the network learns to not focus on one specific feature, but rather use all available information in a distributed form. Dropouts prevent overfitting and make the model generalize better. They are a regularization technique. Dropouts can also be seen as an ensemble approach as they average over a set of possible subnetworks. This technique is applied in many neural networks. Let's move on to the next popular CNN architecture. Stacking layers allows us to capture high-level features by combining the feature maps of different filters. So what happens when we stack many layers, say for example 100? When the CNN gets very deep, the gradients have to backpropagate many layers and many multiplications are performed. As a result, the gradients get very small. This is also known as vanishing gradients problem, and usually the performance decreases when too many layers are added. Residual blocks are simply connections that skip one or multiple layers. In this example, all neurons of the first hidden layer are for instance connected to the third hidden layer. You can see it as a shortcut in a network. As a result, the gradients can smoothly flow over many layers without getting too small. Neural networks that use this mechanism are usually called ResNets. The basic idea of these skip connections is used and extended in many popular CNN architectures. One prominent example is ResNet 50, which has 50 layers and 26 million parameters. With 75.8%, it performs significantly better on the ImageNet dataset compared to Alexnet. You can see how the shortcut connections are added in the identity block. Another thing is that this architecture has only one fully connected layer and uses global pooling, which has been presented earlier. There are further advanced techniques used in different CNN architectures, but it would be simply too extensive to capture all of them in this video series. However, I want to talk about one more thing that was also used in ResNet 50. As you might know, data should be normalized when we feed it into a neural network. This can be achieved by, for instance, standard scaling or min-max scaling. Have you ever wondered why this normalization is done? If the data is not normalized, the optimization of the loss function is more complex, especially if the ranges of the input data are different among the features. Some parameters will be emphasized more than others. As a result, the training of our network takes longer. Through normalization, for instance converting the input distribution to a mean of 0 and variance of 1, we ensure that we end up with a smooth optimization function. But why should we stop with normalization after the input layer? In a network, many activation values flow from layer to layer, and it might happen that the mean and variance of these values changes. This phenomenon is called internal covariate shift. If these shifts are not corrected, the stochastic gradient descent would need to learn the shift as mean and standard deviation as additional parameters. Batch normalization simply normalizes the activation values, so the input values for the next layer, using the mean and standard deviation of the current batch. This means we get a mean of 0 and a variance of 1. This ensures that the distribution of inputs will not change in the network. Overall, the optimization is smoother because the network doesn't need to learn the shift in the distribution from layer to layer. Besides the presented Alexnet and ResNet, there exist many other variants of CNN architectures. For a great overview, I can recommend the website Papers with Code, which provides a large collection of different CNN approaches. Other popular architectures are, for instance, EfficientNets, ResNext, or Inception. In the computer vision area, there are also many other applications where the CNN pattern with convolutions and pooling is used. Worth to mention are, for instance, convolutional autoencoders, an interesting design pattern that is used for many applications. They are able to learn compressed representations of the input image. Another example are so-called U-nets that can be used for image segmentation. This means they are able to automatically extract parts from images, which is commonly used in medical imaging. Finally, another interesting design are generative adversarial networks, or short GANs. They also use the basic CNN layers and basically consist of networks that try to battle each other. One network creates images, the other network evaluates them. There's a website called thispersondoesnotexist.com which shows how powerful this architecture can be. All the images you find when refreshing the page are generated with a GAN, and the person that is displayed does not actually exist, but is randomly created by the neural network. I also encountered some examples where the generation is not perfect. I just wanted to mention a couple of variants in the basic CNN idea for completeness here. There are many things you can do with neural networks. I didn't use it for this video series, but generally if you start a new PyTorch project, I can recommend to use PyTorch Lightning, which is nothing more than organized PyTorch code. This makes it easier to train and play around with the model as well as maintaining the code. You don't need to worry about selecting the CUDA device, early stopping, logging or iterating over the epochs, as this is all done by PyTorch Lightning. Plus, you don't lose any flexibility and keep pure PyTorch. That's it for this part. In the next part we will get familiar with transfer learning and further improve the model. Finally, we will also have a look at explainable AI to better understand our CNN. Thanks for watching, feel free to leave comments if you have questions. See you in the next part.